Okay, let's look at this problem, root to leaf paths. We are given a binary tree and we want to return all the root to leaf paths. For example, this tree have two root to leaf paths, that is 1, 2, 5 and 1, 3. And in order to print out the root to leaf path, we first need to store the leaf to root to leaf path when we travel down the tree. We can use pre-order traversal, and when we travel down the tree, we store the nodes. We just visit it into an array list. Once we hit the leaf node, which don't have any left children, right children, we print out that path. At the first impression, just to use a pre-order traversal, we should be able to print out the path from the root to leaf. However, in this problem, we need to return all the root to leaf paths. So once we print out 1, 2, 5, we are not done yet. We still need to additionally print 1, 3. So how can we do that? We need to use backtrack. So after we print out this, we need to track back to the root. Then we go to the right subtree and hit another leaf, and then we print. This is the code. First of all, we have the data structure for the tree node, which have the value and left children, right children. And in the main function, we just created that tree and get the root node. We create an array list to store the path. Then we call this recursive function, passing the root and the path. At the beginning, the root is 1 and the path is empty. So we go this code, root equal now is not true, root equal left is now, and right equal now is not true. So we go through this code, then we get in here, we add a root value, which is 2, into the path, which is 1 into the path. Then we recursively call the root to leaf, and we pass root left, which is 2, and the path, which has only one element at this point. And this recursive call, go back here, and we check root is not null, and this is not a leaf. Then we go here again, we added the root value, so we added 2 into the path, and we call this line, which is null. Okay, so we go here, it's null, so we return. Then we just go through this line, we go to the next line, we pass the root right, which we pass 5 into the recursive function, and here we check root is null, not true, and we check the root left is null, root right is null, which is true, because at 5 this is a leaf node. So at this time we need to print out whatever stored in the path. At this point there's 2 elements in the path, which is 1 and 2, so we just print that. Additionally, we print the current node, which is 5, and we just print out 1, 2, 5, and we get out of this line. Then we return. After return, we get out of this line and we go to this line. This is most important for back checking. After we finished travel down both left tree and right tree, we need to track back, so we remove the 2 from the path. Inside the path we only have one node, which is 1, and we get out of this function. So we go back, we get the quarter, we get out of the quarter line. We just finished processing the left branch of this root node. So at the root node we need to run the right line, which is here, And let's see, root right equals 3, and the path only have one element, which is 1. And then this recursive core go back here. Root right is 3, so this line doesn't apply, and this line apply because node 3 don't have left children, right children, so it is a NIF node. So we need to print out the element inside the path, which have only one element, which is 1. We print out 1. Then we print out the NIF node, which is 3. So it will print 1, 3. Then we return. Then we get out of this line, and then we go to this line. And we remove the root value, which is 1, out of the path, so the path is empty. Then we return to the caller, which is here, and we are done. In this process, we just print out those two paths. And the backtracking pattern is here. Before we visit the root, so as a current node, we add a current node into the path, then we recursively visit its left subtree and right subtree. After we visit the left subtree and right subtree, we remove the current node out of the path, and we get out of the recursive core. And the caller will continue. Once it's finished the left subtree and right subtree, it will remove the path. Then the caller will continue until we go to the top level caller, and we are done. By doing this, we are able to enumerate all the possible root to NIF paths. And the time complexity is O(n) because we have to visit all the nodes. And the space complexity is bounded by the path length, which is no more than the height of the tree. So the space cost is O(n), is OH, time cost is O(n). This is a problem of return the root to NIF path for a given binary tree.